welcome back to Spherical Chicken in a Vacuum. Today, finally, we get some peace. We don't need to speak about terrible academic news. We can concentrate on what this channel was supposed to be about, which is speak about science and in particular speak about material science. And since this is the first time we speak about material science, I really wanted to start from a definition of material. But there is a huge problem. That was a big mistake on my side. It's not that easy. I don't really know what a material is, and there are hundreds, maybe thousands of different definitions around the web. So let's talk about this. Let's start from the question: what is a material? And if we go to this vocabulary, Italian vocabulary, I'm Italian, so that's why you see that. Well, there's a lot of wall of text here to read, but yeah, the concept is not this easy. And even if you pick different scientific books, they will give their own definition based on how they think, how the author thinks, how the author approaches the topic. And I don't want to say that they are all wrong. I just want to say that they're all partial. They don't have a give you a full view of what a material is. And I will also don't give you a full view of what a material is because there's too much. But I want to give you my definition, a definition that I will use in this series of lessons. Okay? So let's start from something easy, something that we all have at home, like a gold ingot. And if we have a gold ingot, we can see that it's basically based on two different things. One is the design, so the shape, and we can throw that away. It's not something we will discuss about now. And something else is gold, so the chemistry of the thing itself. Gold element symbol is AU, which stands for aurum from the Latin language. And if we have a look at what is defined aurum with gold, we see that is this really nice atom with 79 electrons, 79 protons, and 118, I think, neutrons. And this is it. Can we call this the material? Well, it's a little bit too little for what we intend. There's more, because the atoms then are arranged in a structure that is a crystal, and in the case of gold, it's usually this nice cube with an atom of each corner and plus atoms on the middle of each of the faces. This is a really nice packing. I think it's a 74% full, so one of the best packing that we can obtain by putting together spheres one on top of the others. Okay. So is this crystal what the material of the gold bar is? Well, still not enough. Of course, this is the material, but it's not enough because these crystals are then arranged in what is called a microstructure, which is made of different crystals with different orientations. Each crystal is surrounded by the grain boundaries. You can see the lines there. So is this microstructure the material? So we can say that this is the material that makes the gold bar. Again, yes, but there is something more. And to see what I mean, we need to switch to another material, because this was a nice case of something that was made one phase. In reality, things can be a little bit more complicated. So let's move to this. This rail is made, of course, of steel, and this type of steel contains 0.84% of carbon. So iron and carbon are the two main components of this steel, even if in reality there are other elements that account for more than the content of carbon. But what gives us the properties of the material itself is mainly the structure of iron and carbon that combined together gives us this strange thing, this strange microstructure that it doesn't look like the microstructure of gold we had before, because here we have stripes of white and black. So what are those stripes of white and black? If we had a look at the structure, they are overlapped layers of what is called a cementite and what is called alpha ferrite, one on top of the other, stacked like this. and each stacking of these layers makes one grain. So we don't have one phase like before. For gold, everything was the same type of crystal. Now we have crystals that contain two different phases. One is cementite, which is a type of iron carbide, and one is the soft ferrite. Okay? And things are even a little bit more complicated because starting from the same combination of iron and carbon that gives us that nice structure that is called perlite, we can also obtain two other structures, either martensite or bainite. And these two structures are chemically very close to the perlite. They're made with the same components at the same concentrations. What changes is how fast we cool it down when it's melted. And martensite is hard and brittle and a metastable phase, and bainite is something in the middle between the perlite, which is the stable form of the steel, and martensite, which is the metastable form. And it's very difficult to obtain a good bainite, but it's the phase that has the best properties, overall properties. So we have materials with one phase, materials with many phases, and we cannot say that this material is in reality two materials. It's one material with two phases, even if by itself each phase can also be a material. Complicated. Well, let's rewind it a little bit. We have things like gold or even copper. We can make pure gold, pure copper. Then we have alloys like bronzes or steels, etc., etc. And this can have more than one phase. And then we have materials that are even more complicated. And wood is a good example. Wood have many phases, many chemicals, many different types of molecules inside, even water. And the water is very important for the properties of wood. So there are many phases inside, and this is still one material. And also, there's something about structure for wood, and you know that depending on the direction of wood, the properties are different. This is more, even easier to see if we take something like fabric, where there is a structure, right? And the point is, this structure can also be considered part of the material itself. For example, think about foams or sponges. If something is made of sponge, we don't say it's made of the element that makes the sponge, like for example cellulose. We say that it's made of sponge, so we consider sponge to be a material with this structure, with this porous structure, even if the stubs of the sponge, the hard part of the sponge has its own chemical composition, and the other is just voids. So there's something of structure, like in wood or in fabrics or scaffolds or sponges, foams, etc., that enters in the definition of material. And I want to give you two more examples. One is this. This is a really nice electron beam melted structure of titanium. So can we say that the material of this structure is titanium? Yes, but it's a special type of titanium if you want. It's a trabecular titanium. And this structure with these porosities is made in order for the bone to be able to grow inside. This is a biomaterial. This is used for implant application. It's like a sort of synthetic bone, if you want, or bone scaffold for bone integration, bone regeneration. But we will speak about this much later in another lesson. What I mean is that the basic structure with these porosities that can repeat it like a matrix in all directions, this is also material because it influences the properties of the object itself. Same goes for this. This is a two-dimensional structure that I 3D printed. We can say that it's just polylactic acid, okay? But also the fact that it's made with these spirals influences the properties. So we can make objects using the spirals as units. So the spirals by themselves are also a material because they influence the properties. So just to summarize everything and try to give you a comprehensive definition, okay? These are just objects that I have lying around my desk. On the top, we have a femoral head, which is made of this is zirconia, tougher than alumina. And so there are two phases. One is alumina, one is zirconia. In the microstructure there, you see there's white grains of zirconia in a darker matrix of alumina. And if I take a sample of this femoral head with this structure, so as big as the image, that is representative for the whole structure. So I can predict the properties of the femoral head by knowing the properties of this piece of femoral head. So we can say that this is not two materials, zirconia and alumina. This is a mixture, which is zirconia, tough, and alumina, that has this structure, and using a sample of this structure, we can predict all the properties. So the material is zirconia, tough, and alumina. Same goes from the cat there, which is made of alumina. It's only one phase theoretically, but in reality there are porosities and there are things at the grain boundaries, etc. So in this case, again, the image we have is more or less representative for all the properties because we know how big the grains are, and this also influences the properties. So this is a sample. A sample of this size can be used to predict the properties of the whole cat. Okay, mechanical properties, chemical properties, etc. For the trabecular titanium in the bottom, the structure itself is this sponge of titanium. And if I say that it's made of titanium, I'm not wrong, but people can imagine a block of titanium, and titanium does not help us to predict the properties, to say just titanium alloy, this is titanium 6 aluminum 4 vanadium. Just to say that does not help us to predict the properties of the sponge because it's much softer than a pure 100% block of titanium would be. And if we take a sample of the size of the image that we have in the bottom right, this is obtained by a scanning electron microscope, of course. This sample is big enough to predict the properties that any object made of this titanium sponge have: mechanical properties and chemical properties, etc. Okay, so that a technically useful definition of material is the smallest portion of a solid that can be used to predict, well, maybe not all, but most of its properties. Okay, so if you take a sample that is small enough but not too small enough that but still can be used to predict the properties. So if you go too in the small, for example, you go to the atomic size side for size for alumina, then you cannot predict the properties of the whole manufacture because you don't have information about the crystal structure, etc. If you zoom too much on the zirconia or in the alumina, you cannot predict the properties of the composite material that has both phases. For the titanium, if you zoom too much on the titanium, you lose the properties that are that we obtain thanks to it being a sponge. So the smallest sample of a material, of object, that gives us an overview, a prediction of the properties of the whole object. That is a functionally useful engineering definition of material. And with this definition, we will continue to discuss about material science. And if you don't agree with me, well, let's discuss about it. But we can also change the definition if you like. Okay? See you next time. Goodbye.